Yeah, welcome to Massive Open Online course on chemical process intensification. So, in this module, microprocess technology in process intensification, we are discussing something about that introduction and also what are the different applications of microprocess technology. So, in this lecture, we will try to go through about some hydrodynamics and transport in microchannel based microreactors. So, we will discuss that hydrodynamics of gas liquid flow in the microchannel based microreactor and also what is the mass transfer of gas liquid flow in the microchannel based microreactor. Now, as we already discussed about that what is the definition of that microprocess technology and also what are the different types of micro reactors and they are that how they are designed and also how to actually fabricate all those microstructure reactors that we already discussed in brief in our earlier lectures. And they are also told that the execution of the chemical process in the microchannel based reactors will be that in a small volume, typically inside a channel with diameter less than 1 millimeter, and chip based reactor is dealt with the operation of large number of parallelized micro channels in a compact volume. And then we have discussed about that what are the different applications of that microchannel based reactors, even other different types of reactors that we have discussed in our previous lecture. So, in this lecture we will try to go through some hydrodynamic aspect like what is that criteria to actually develop microchannel based microreactors, what should be the channel diameter and also what will be the flow pattern and void fraction, what should be that in the microchannel based reactor, and what will be the frictional pressure drop, how to analyze it, even what are the different mixing characteristics, that is main that intensification criteria in this microchannel based reactors, and also size distribution of the bubble in case of gas and droplet in case of liquid, in liquid distribution, interfacial area. So, these are the different hydrodynamic characteristics in microreactor channels. Let us try to understand that what should be the criteria for that microchannel based microreactor. You know that the criteria of microchannel have been proposed by several authors in different ways, but roughly given by that Laplace constant lambda or the Edwards number by that Su et al. In 1964, still it is being used for that design of that microchannel reactor based on this criteria. Where you will see that this lambda is called that Laplace constant and EO is called the Edwards number. This lambda is defined by this equation here shown in slides. See, lambda will be equal to root over of sigma by this g into rho L minus rho z, whereas this Edwards number this is g into delta rho into d square by sigma, where sigma is called surface tension of the liquid and rho is the density and delta rho is the density difference of these two immiscible fluids, like here if it is gas and liquid should be then rho L minus rho z, and d is called the diameter of the channel. If it is cross sectional, if it is that rectangular channel, then there should be a hydraulic diameter to be considered, and also if it is suppose circular channel, then of course it is diameter will be that circular channel diameter, hydraulic diameter will be the same. And so, as per this Su and Griffith 1964, they derived this following criterion for the tube diameter d for that microchannel based reactor development. Here in that case, confined diameter should be lambda by d, that should be greater than is equal to 3.3. So, whenever you are going to consider that microchannel, it should be of course that in a criteria that lambda by d always should be greater than 3.3. So, if you are considering that the Laplace constant here, it should be corrected like this k, it is not the k, it is generally it is lambda. So, please correct it here, instead of k it will be lambda. So, here this is lambda. So, this is lambda is called Laplace constant, and in case of that if you are having that this d is equal to that if suppose lambda by is greater than or equals to 3.3, then you have to consider that lambda it should be equal to 2.7 for air water flow at 0.1 that megapascal. So, in that case what should be the d will be around 831 micrometer. So, so in this way that if you are considering that exactly equals to 3.3 for this Laplace constant of 2.7, then you can say that this microchannel diameter should be of course less than 831 micrometer. Other way also this you can define that microchannel where Edwards number should be less than equals to 2 pi whole square. So, that is given by Breuner and that Meron in 1992. So, in these two criteria can be used for that having that microchannel or define that microchannel based microreactor. Now, what are the different flow regimes in microreactor channel? You will see as per reported in literature that 4 main flow regimes are generally observed, like bubbly, slug, annular and slug annular flow. And in microchannels of order of a few micrometer to a few tens of micrometer, two phase flow is believed to be influenced mainly by surface tension, viscosity and inertia forces. So, based on which this due to the that interfacial area or surface of this gas liquid or liquid liquid phases, just that making different shape as per those these different types of flow patterns are obtained in microchannel. Like here it is shown that different criteria of or different operating condition of having these 4 types of flow patterns, like bubbly flow. You can have this bubbly flow regime in this region in this map. Here this map is actually formed by superficial liquid velocity versus superficial gas velocity. In this case you will see that if you increase the superficial gas velocity and also accordingly superficial liquid velocity as per this that scale, then at this region you can get that bubbly flow, whereas you can get that stratified flow in this region. Here stratified flow means here one fluid will be flowing over the other fluid, mainly that dispersed fluid, that is lighter density fluid will be flowing over the density of higher density liquid. So, in that case you can get that at very low liquid velocity and low gas velocity, you can expect that there will be a that stratified flow, where that both the phases will be separately flowing, having one above other. So, in that case you can you can maintain this stratified flow only just by controlling this gas flow over the liquid flow. So, and also you can get that slug flow, where that you will see that liquid if it is single phase, you will see that liquid will be breaking up and there will be discrete way of flowing of that liquid as a slug. And if it is on gas liquid flow, you will see there also there will be a a successive breakage of that gas slug and liquid slug, and it will be flowing through the channel. And another is annular flow, where you can say that heavier liquid maybe that flowing adjacent to the wall of that channel, whereas at the core regions there will be a flow of lighter liquid. So, this is called annular flow. So, again this other flow also you can have that wavy flow, sometimes that stratified flow. If that gas flow rate is higher, then you can expect that there will be a wave formation of the interface of that gas and liquid. So, that is called that wavy flow. Now, you will see that sometimes that liquid also will be flowing as a ring through the channel. So, it is also sometimes called the liquid ring flow. Even some lump amount of liquid will be flowing through the channel, and after a certain length it will be breakage, and also it will start again for continuous that liquid slug. So, it will be called as that liquid lump flow. So, there are that liquid lump flow or that liquid ring flow, it will be coming under that in the annular flow regime, and also at that higher flow rate of liquid flow, and also higher gas flow rate. So, this is the thing. So, in this region you can get that ring flow of that liquid here, and also here at this region you can get that annular flow where that liquid lump flow will be there, and that liquid lump flow and liquid ring flow will actually be consisting that annular flow there. So, this type of different types of flow pattern you can get in the channel, that is micro channel based microreactor. So, it may be sometimes useful because this at different flow pattern you can have that different efficiency of that mass transfer, even extraction, even other chemical engineering process, even at reactions also even you can get that different reaction performance at different flow pattern. So, you have to know that different types of flow pattern in the channel. Now, void fraction is also one of the important parameter in that assessing that mass transfer efficiency or mass transfer performance there, because it depends on that void fraction. If it is suppose gas liquid operations, if suppose gas is absorbed in a liquid medium, then you can have more interfacial area if your void fraction is increased there. So, there are several methods actually are available to find out that void fraction. Mainly in microchannel based reactor, a constant current method can be used to measure that void fraction. It is actually proposed by Karioszewski here in 1991, and also as per their experimental results, they have suggested some correlations to actually predict that gas hold up in the channel. So, according to their observations, that if suppose that certain constants, they are beta is less than beta A, then alpha should be equal to beta. What is that beta? Beta is nothing but that gas volumetric ratio beta. So, gas volumetric ratio means here what is the volumetric flow rate of the gas upon what will be the total flow rate of the gas and liquid. So, it is denoted by that beta. So, in that case volume fraction should be equal to alpha is equal to beta, that means volume fraction will be equal to gas volumetric ratio if that volumetric ratio is very low. Whereas, if this volumetric ratio is less than 0.6, then you can expect that this void fraction will be equal to 83% of that gas volumetric ratio. Again, if this volumetric ratio, if it is greater than 0.6 and less than 0.95, then you can expect that this void fraction of the gas will be equal to 0.69 into beta plus 0.0858. So, by these correlations you can calculate what should be the void fraction. Even if your volumetric ratio, that is beta, is more than 0.95, in that case you can predict that void fraction by this correlation as given by this Kawasaki et al. In 1991. So, these correlations is very useful to calculate that void fraction if you know that gas and liquid flow rate in your operation. And also pressure drop is also one of the important aspect of that design of that microchannel based reactor, because based on this pressure drop there will be energy dissipation, and based on that energy dissipation how that mixing is happened inside the microchannel. This is one of the important aspect there. So, that is why you have to know that what should be the frictional pressure drop inside the microchannel, and how to analyze and how to predict that frictional pressure drop. Now, the two phase this pressure drop across the channel test section that can be measured by conducting experiments to account for the additional pressure drop across the test section, as well as some contraction and expansion losses at the inlet and outlet. So, whenever you are going to measure this pressure drop in microchannel, you see that is you have to be very careful about that whenever liquid is flowing through that microchannel, and before entering that microchannel, of course, these two fluids are coming from that two pipe entry. So, in that case that pipe entry, whenever it will be coming to and join to a one point, and from there that channel will start. So, you will see that there will be a change of cross sectional area from that two inlet to a one channel inlet there. So, in that case of course, there will be some contraction or expansion of factor that should be also considered there. So, due to that a contraction and expansion losses in inlet and outlet also, you will see there will be a additional pressure drop across the test section there. So, that should be also considered in your calculation. So, in that case the total experimental two phase pressure drop, it will comprised of the pressure drop due to the effects of friction and acceleration in a single channel of known length. So, it can be calculated like this. This is your experimental total two phase pressure drop, that will be you know that the summing up of this frictional pressure drop of that two phase, and also additional pressure drop that is due to that that expansion even or contraction losses. So, according to this, if this additional pressure drop that can be calculated by this equation here, this is simply that by that momentum balance you can have, where this can be calculated by this g square here in terms of that mass flux, even mass quality of the gas, even density, even volumetric void ratio, these things. So, at the inlet and outlet, what should be this this component of this equation, and what should be the in the outlet component of this here. In this case, x is called that mass fraction of the mass quality, or you can say mass fraction of that gas of that gas liquid mixer, and rho is the densities, is the mass flux, that is density into velocity that you have to calculate. So, by this equation you can calculate what should be the additional pressure drop due to that contraction and expansion losses. Now, contraction losses at the inlet actually is estimated using the loss coefficient, that is Kc, that Kc will be equal to 0.42 into 1 minus d1 by d2 whole square, where d1 should be less than d2. In this case, d1 and d2 are the diameters at the section 1 and 2 respectively. So, this head loss or you can say that contraction losses at the inlet can be calculated by this equation, because it is required in that case, because that frictional pressure drop actually that depends on this expansion and contraction loss coefficient and loss there. And the head loss at the channel outlet due to the sudden expansion can be estimated with the loss coefficient Ke, that equaling unity, since the channel outlet for the single phase measurements is directly exposed to the atmosphere. By subtracting these losses from the experimentally measured pressure drop, that is delta P S P E X P, that we have given in our earlier equation there, that this experimental the single phase frictional pressure drop can be calculated by this equation here, where in this case K should be the expansion coefficient. That expansion coefficient will be equals to 1, because in this case channel outlet for this single phase measurements is directly exposed to the atmosphere. That is why this Ke expansion loss should be equal to 1. Whereas, in this case you will see that this single phase frictional pressure drop, that is F is for friction here, single phase frictional pressure drop, it will be actually what should be the measured frictional pressure drop, that minus this that expansion or contraction losses there. So, in this way you can calculate what should be your total frictional pressure drop as per experimental data. After that, what should be the friction factor for the single phase flow, you can calculate by this equation as per Fanning equation here. This will be, or you can say it will be that 2 into delta P S F into F d by rho L u square. So, this friction factor is actually that Darcy friction factor, and this Darcy friction factor will be actually depending on that Reynolds number, and it will be that 64 by Reynolds number if your flow is laminar in condition. And how to analyze this two phase frictional pressure drop? That Lockhart Martinelli in 1949 they have given that concept for analyzing that two phase frictional pressure drop based on that single phase frictional pressure drop. They have actually expressed that what should be the multiplication factor of this two phase frictional pressure drop based on that that single phase pressure drop. And that two phase frictional multiplication factor, it is called the two phase friction multiplier, which is actually denoted by this phi L square. And also another parameter as per their model, that this is actually the ratio of the frictional pressure drop of single phase pressure drop continues to single discrete phase. So, in that case that this parameter is denoted by x. It is actually defined as the square root of that ratio of frictional pressure drop of single phase continuous to the single phase in discrete phase. So, that according to that two parameter, that phi L and x, you can assess that two phase frictional pressure drop. Now, according to that Lockhart Martinelli models, this concept is like this. This is your two phase frictional pressure drop. This will be some multiplication of single phase frictional pressure drop. It may be delta P T P F, that will be the phi z square into delta P G F also. So, in that case it will be that two phase friction multiplier for gas and two phase multiplier for liquid here as phi L and gas for phi z. So, this is the main concept, that if you are considering the single phase liquid pressure there, then it will be denoted by delta P L F, frictional pressure drop of single phase liquid, and if you multiply that factor phi L square with this delta P L F, then you can have this two phase frictional pressure drop. Now, what should be that single phase liquid frictional pressure drop? That can be calculated by this equation, and where here F L is still called that Darcy friction factor, that can be calculated by this equation. And also, if you are considering that gas phase, then gas phase single gas phase frictional pressure drop can be calculated by this equation, whereas this F g is called that friction factor of the single phase gas. This is Darcy friction factor of that single phase gas, which will be calculated by this equation. And also x square, that is the Lockhart Martinelli parameter x, is defined as that x square will be equal to delta p LF by delta p GF. So, it will be actually after simplification it will be coming at phi g square by phi L square, whereas Sholm they have given Sholm he has given that phi L should be actually related to that Lockhart Martinelli parameter x, and it is actually expressed by this relationship that phi L square will be equal to 1 plus C by x plus 1 by x square, where C is called the Sholm constant, and this Sholm constant actually depends on the physical properties of the fluid as well as geometry of the channel. Now, if you are considering that water or amine flowing through the channel with air, then you can say that C will be or C can be calculated from this correlation here for water and this for amine. It is suggested by Ghanavati et al. In 2015, and they have published in Chemical Engineering Journal. So, according to their calculation, according to their correlation, you can easily calculate what should be the C. And if you substitute this C for a particular operating condition in this equation, then you can calculate what would be the phi L square, that is two phase multiplier, friction multiplier. Once you know that two phase friction multiplier, and then if you multiply it by this that single phase liquid friction factor, then you can have that total frictional pressure drop in the channel. So, based on this equation you can easily predict what should be the frictional two phase pressure drop there in the channel at a particular operating condition. Now, later of course, very interesting, and also they have actually correlated that frictional pressure drop with that mixing characteristics. Now, what is that mixing characteristics? That many unsolved challenges remain in the field of mixing in microchannel. In that case, the diversity of the mixing task is large, and so is there that industrial importance, and mixing is a good example how that equipment dominates the type of processing solutions chosen here. So, in this case you have to remember that design and development cycle for mixing field based design, there is a selection of mixing equipment based on the process requirements. So, it is very important to actually remember here. Now, one important term, it is called mixing fields, that is related to the rate and scales of the segregation. Destruction demands that greater variety of equipment solution for the specific mixing task. Example for the industrial applications like rotor stators type mixing equipment, static mixers, multi-shaft mixers, extruders, microstructure mixers. So, these are the different that device based mixing equipment or that for that having that micro mixing in a particular devices, and this is actually denoted by that mixing fields, and it is related to the rate and how that mixing will be happened, and what will be the effectiveness of the mixing, and what should be the scales of segregation there, and how that scales of segregation restrictions actually changing that mixing pattern and mixing tasks in that particular micro channel based reactor. Now, what should be the drivers for that mixing in the micro spaces? We are talking about that micro channel based reactors. Of course, that in that very small volume or micro spaces, you can say that many passive microstructure mixers that follow the design principles used of the micro scale of static mixers with internal packings. It has some advantages, some compactness and low capital cost, low energy consumption and other operating expenses, lack of penetrating shaft and seals there. You will see narrow residence time distribution you can expect, performance independent of pressure and temperature. Sometimes the narrow residence time distribution also you can expect, low energy consumption and other operating expenses will be there. So, these are the drivers for the mixing that having in the micro channel based reactor or micro scale based devices. to get intensified mixing there for the process intensification. Now, specific chemical engineering drivers for that micro mixing, like it enables that mixing where mixing will be under the laminar flow conditions, and that is valued by conventional mixers. And also in this case, in chemical engineering drivers for micro mixing, it will give you the fast mixing for even faster reactions in the chemical synthesis, mixing at only small overall internal device volumes, mixing of a flow of high structural regularity, where that you can improve the scaling and numbering up also. And in this case, you will see that laminar mixing of viscous media has most microflow processing there, because all those things are actually in favor of that micro processing and also that process intensification in specific chemical engineering application. Now, what are the mixing principles that in the channel whenever fluid will be flowing, that two phase flow will be there? What should be that principle of mixing by different mechanisms that what we have discussed that in the field, like rotostators, static mixers, multi-shaft mixers, extruders, microstructures mixers. So, in this industrial applications of different type of micro mixers, based on different principles how it will be working, that we have to know. Because if you are considering that different types of micro mixtures, that whether this diffusion process will be enhanced or not, whether that limits of the diffusion mixing will be improved or not, whether there will be any other different types of flow is produced or not, whether it will be that secondary flow or convective flow patterns are imposed on that channels or not, what will be the superposed capacity of the flow on the other flow of this other liquid, there is there any recirculation patterns or not, chaotic advection or swirling force are there or not. So, based on that you can assess that mixing in that particular devices, and because of which you can get that process intensification of the mixing in the microchannel devices. So, that mixing principles rely only on two principles, which are diffusion and convection. So, diffusion between short distances establishing high concentration gradients, and also the diffusion has some limits like robustness, that will be fouling, and also cost. Complex microfabrication is one important factor there. Now, to overcome these limits by diffusion mixing, the induction of the secondary flow like convective patterns which are superposed on the main flow, sometimes recirculation patterns, chaotic advection, swirling flows, even that Dean flows are also developed to have this. Now, convection is effective for mixing, since it serves to enlarge mixing interfaces. Convections of gross mass portions that can be used at a much larger scale to steer even complete chamber volumes. Some other means also you can get that micro mixing there in the devices, like ultrasound, some other electric field also can be applied to get that micro mixing also. At high Reynolds number, you can have turbulent mixing that can be also utilized just by making a mechanical provision to the channel, so that you can get high turbulence at high Reynolds number, and also intermixing will be more there. Now, what will be the means for that mixing of micro spaces? There may be some devices that may actively giving that mixing process, sometimes passively. So, there are two means of mixing that can be classified as that either active or passive. Now, passive micro mixer means use part of the flow energy for the feeding, and thereby generates that special flow schemes with ultra thin flow compartments, such as lamella for diffusion mixing, or utilize that chaotic advection by secondary flows to enlarge the interfaces. Now, devices that relying on passive mixing utilize the flow energy, maybe due to the pumping action, due to the hydrostatic potential, due to restructure a flow in a way which results in faster mixing by some different means, like you can get that passive mixing by split and recombine of the flow, and also you can have that by chaotic from the super imposed recirculation flow patterns. You can have that mixing by the injection of many substreams via an array of nozzles. You can get that passive mixing by the turbulent mixing as if by collision of jets there. So, other also principles of having that micro mixing, like it is called active micromixing process, and it relies on moving parts or externally applied force that will give a that fluctuations in the that fluid elements, and based on which there will be a intensified mixing in the fluid device. So, that is why that external energy that give you that micro mixing, and that is why it is called as active micro mixing process. That external energy, what should be that external energy? That may come from ultrasound source, that may be acoustic, that may be bubble induced vibrations, that may be electrokinetic instabilities, that may be periodic variation of the flow rate, that may be that small impellers or micro impellers you can say, and that may be magnetohydrodynamic action, that may be due to that piezoelectric vibrating membranes, that may be electrowetting induced merging of droplets. So, these are different way of producing external energy by which you can have that micro mixing in a micro channel based reactor or other micro reactors. Now, what are the application fields and the type of the micro channel based mixtures there? So, application field of micro channel based mixtures includes both modern and traditional you can say, and also you can have that micro mixer elements, chip like micro mixer, microstructure mixers there. And chip like micromixer compartments like micromixers are employed for the more conventional chemical and chemical engineering applications at the laboratory scale, whereas microstructure mixers typically comprising microstructures in a large housing, and micro mixer elements, micro mixers, microstructure mixers typically have flows in the range of millimeter per hour, that is 1 liter to 1 liter per hour, and also 1000 liter per hour ranges respectively. So, in that case we can have these different applications within a certain range of that micro mixing efficiency based on that channel structure. Some important active mixing like electrohydrodynamic translational mixing can be accomplished by electric forces here, when fluids with different electric properties such as conductivity and permittivity are exposed there. In microelectric mechanical systems, the electric fields of relatively large amplitude can be generated by means of low voltage, so that respective mixing effects can be improved, or you can have that more influence of to get that mixing phenomena. Electric force mixing is adequate of mixing flows at very low Reynolds number, whereas this may be parallel or perpendicular to the fluid interfaces this field, and in the presence of sufficiently large electric field, a transversal flow secondary flow can be steered. Direct DC and alternating currents can be applied for this purpose, and this AC has oscillating frequency, and example of like square or a sinusoidal type. So, this that oscillating frequency will generate that micro mixing, or will govern that, or will enhance that mixing processes there. Secondary flow lateral to the flow direction can be achieved by in this case specially homogeneous or inhomogeneous fields respectively, that termed as electrophoresis or dielectrophoresis, and electric field may interact with flows fed by hydrostatic or pumping action. Flows driven by electroosmotic means may be mixed as well as the action of fluctuating electric fields which creates oscillating electroosmotic flows and has been termed as electrokinetic instability. So, electrohydrodynamic micromixer is also one of the important development of that micromixer for that intensification of this mixing process. In this case, it is generally comprises of a simple T channel structure, and in this case a electric field perpendicular to the fluid interface is generated, and the electrode's phase is other with a differential potential between the two sets, one set grounded and other sets will be energized. So, based on these principles this mixing happened, and this electrokinetic instability, electroosmotic flow micromixers also there. In this case electrokinetic instability mixer is driven by electroosmotic flow and thus termed as EKI-UF micromixer. So, in this slides it is given that how you can design a electrokinetic instability UF micromixer there as per Hessel 2005. In this case, two fluids to be mixed come from the two ends of the shorter channel and merge when entering the longer channel and moving along it, and you will see that based on that interaction of the fluids there will be intermixing or micromixing. And electrokinetic instability electroosmotic flow micromixer, this is can be also enhanced there. In this case, two channels are arranged crosswise there, and I will see that each having two reservoirs at the ends as shown in figure here according to that Kumar et al. 2011, and in this case the two liquids are pumped into two fed channels which merged in a Y type configuration, and from there they flow co-currently in one channel and are collected in one reservoir. At the beginning of this channel you will see there will be a quadratic chamber intersects in which the flow is mixed by this electrokinetic instability action, and also the chamber is connected to channels with two reservoirs at their ends, and these reservoirs are each in contact with the electrodes which are connected to a high voltage amplifier coupled with a function generator. So, in this way this is the steps by which you can have this micromixing by this electrokinetic instability action. Also electro-rotational mixing also one of the important other mixing principles there by which you can have that micromixing inside the microreactor. In this case electro-rotation is actually done, and this is done as a consequence of the induction of dipole moments and torque exertion by a rotating electric field. And in this case coupled electro-rotation uses static external fields which are specially fixed to induce dipole in two or more adjacent particles there. Also magnetohydrodynamic mixing also another important mechanism by which you can have that micromixing. In this case a microchannel is equipped with an array of electrodes which can generate a complex electric field by alternate potential differences. In this case the currents are induced in various directions, and the electric field that can be coupled to a magnetic field that will yield you that some Lorentz body forces for the liquid mixing, and that Lorentz force is actually the force that is exerted on a charged particles moving with the velocity through an electric or magnetic field. So, by this mechanism also you can have that micromixing phenomena. Now, another important micromixing phenomena is called air bubble induced acoustic mixing. An air bubble here in a liquid medium can act as a actuator. In this case the bubble surface that will behaves like a vibrating membrane when it is energized by an acoustic field, and in this case the bubble actuation is largely determined by the bubble resonance characteristics, and the bubble vibration is due to that sound field that is induced, and that induction actually based on the friction forces at the air liquid interface, and that cause a bulk fluid flow around the air bubble, and because of which you will see there will be a interface fluctuations, and based on which you can say that there will be a acoustic micromixing, and this type of phenomena is called that that cavitation microstreaming, or you can say that acoustic micromixing. And circulatory flows around that bubbles that lead to a global convection flows with a tornado type patterns which enhances the mixing there. Ultrasound aided mixing is also one of the important aspect of that micromixing that can be achieved by ultrasound using lead zirconate titanate or a piezoelectric ceramic operated in the kilohertz regions as given or reported by that Kumar et al. In 2011. In this case, liquid streams can be moved and even turbulent like eddies are induced. Favorably, you can say that ultrasonic action is coupled into a closed volume a micro chamber. Other different types of micro mixing like valveless micro pumping, micro impeller mixing, they are even magnetic micro-bead micromixer, Y and T type configuration diffusive mixing, and also cross injection mixing with square static mixing elements, jet collision turbulent or swirling flow mixing, other different micro mixing here, double T junction turbulent mixing, serial diffusion mixer for concentration gradients, cantilever valve injection mixing, recycle flow mixing based on eddy formation, recycle flow Canada effect mixing based on Taylor dispersion. There are several other different types of micro mixing are there. Micro-bead intersticks mixing, bimodal intersecting channel mixing, mixing by helical flows in carved or Minder microchannels. So, these are other different types of micro mixing mechanism are there. So, here in the tabular format we have given here the different types of micro mixture that may be active, passive, and how it would be differentiate there in this table. So, please go through this and Kumar et al. He has described in details all those process here. Please go through that paper if otherwise through the slides you can have the idea what will be the micro mixing mechanism. Now, performance and comparison of the micro mixer. Of course, there are several different types of micro mixers there. Now, you have to analyze that performance or comparison of the micro mixers, how to analyze that. So, in this case mixing time is used to characterize the mixing in a micro mixing device, and the homogenization of the components that will be based on the mixing by energy consumption and the pressure loss within the device. And fast mixing within a short range is a desired effect of mixing. To characterize the achievement of the effects, the ratio of performance of the effort that gives a reasonable value to compare different devices. In this regard, to some identification numbers for micro mixers, the mixing effectiveness ME1 and ME2 are introduced there by Kochman et al. 2000. So, based on which you can analyze that performance of the micro mixer. So, according to that Engler et al. 2004, the mixing effectiveness is constituted by the performance of the mixing process, that is divided by the effort that has been actually put into it. The performance of the mixing process is determined by the ratio of the hydraulic diameter to the mixing length, like as shown in here slides. By this equation you can have this what should be the hydraulic diameter and the mixing what should be the ratio of that hydraulic diameter to the mixing length. And then if you know that hydraulic diameter and the mixing length, the effort of the mixing process can be characterized by this Euler number, and with this the ratio of this hydraulic diameter to the mixing length, and this is a measure of the pressure loss in relation to the flow velocity. So, this mixing effectiveness can be calculated by this equation if you know that pressure drop and velocity and also this hydraulic diameter and the mixing time there. And again, if you know the that mass flow rate, based on that mass flow rate also you can calculate with that frictional pressure drop there. So, based on which you can calculate this mixedness of this effect of this microchannel mixer. And if you are having that less mixing time there, of course, that mixedness will be effectiveness of the mixing will be increased, and if you have the more frictional pressure drop also, you can say that mixing effectiveness will be less there. So, according to this you can easily assess in which cases that or which mixers will be with the relatively higher effectiveness of the mixing there. And you will see there Kochman et al. 2006, they have compared this different mixtures based on the Reynolds number, and this effectiveness of this mixing actually that if it is increased with that Reynolds number, if it is increased, of course, that higher flow rate will give you that more mixing there. But you will see that this here as per figure shown that 3D T mixer will give you that relatively less mixing compared to that tangential mixer if your Reynolds number is considered to that keep it constant there. So, that is why that different mixedness factors will give you that assessment of the mixing efficiency of the channel based on this. And mixing effectiveness can also be expressed in terms of energy dissipation, like here by this equation you can express this mixing effectiveness. If you know that energy dissipation depends on that pressure drop. This pressure drop will give you that what will be the that energy dissipation through the channel, and once you know that energy dissipation you can easily calculate this, where this that kinematic viscosity, this nu is kinematic viscosity, epsilon is called energy dissipation, and this Tm is the mixing time, and R is the Reynolds number. And the ratio of the kinetic viscosity to the energy dissipation is a time scale that will measure in a fluid dynamics of convective mixing isotropic turbulence, and the square root of that ratio of that mixing effectiveness to the Reynolds number gives a measure or a comparison of two mixing times there. Also, for the high throughput devices, that how to calculate that mixer effectiveness there. In this case, that mixing effectiveness for that particular mixer can be extended by that Reynolds number here as per this Me1 into Re, that will be regarded as Me2. So, it will be calculated by this equation as shown here in the slides there. And so, by this equation you can calculate what will be the mixing effectiveness for the high throughput devices. And here in this figure there is some that comparisons are given for different micromixers are there, and based on that effectiveness, mixer effectiveness for that high throughput equipments there, and you will see that for asymptotic T mixer is giving the maximum mixer effectiveness there. And then mass transfer. Mass transfer, of course, based on this mixing characteristic that you can analyze that mass transfer, higher mixing will be of that more diffusion, more that effectiveness of the mass transfer there, because in this case there is no back mixing that may sometimes hinder that mass transfer efficiency, but in the microchannel based reactor there will be no you can say that back mixing. So, in that case you can increase the mass transfer by this channel. Here some characteristics of the channels dimension and the application of the mass transfer with gas phase of carbon dioxide, nitrogen, hydrogen sulfide with that different liquid solvent like water, sodium bicarbonate, even sodium hydroxide, even methyl diethylamine, even diethylamine also. So, these are the different studies of that mass transfer in the microchannels for gas liquid system. And there is a need to evaluate that predictive accuracy of the available two phase pressure drop models at small hydraulic diameter, as the case in the microreactors, because this actually directly influences of the mass transfer characteristics in the channel. So, here some reaction systems of that absorption of carbon dioxide in a diethylamine in microchannel and its mass transfer. Here, as per reactions, how that reactive mass transfer will happen with that carbon dioxide to that diethylamine. And in this case, based on this, you can say what will be that absorption rate there, that can be calculated by this equation. And then that absorption flux will be calculated by this equation once you know that molar flow rate at the inlet and outlet in the channel. And mass transfer coefficient can be calculated from that it is called that absorption flux, that is NCO2, and if you know that concentration gradients, they are as per mass transfer principles. So, that you can calculate from this equation that concentration gradient, and accordingly that mass transfer coefficient you can calculate. And this mass transfer coefficient you can calculate in terms of that pressure also, that concentration, because this concentration you can calculate in terms of pressure, because that at the partial pressure at a given location, it can be calculated based on the mole fraction and the absolute pressure. So, according to the Henry's law, that you can calculate what will be the partial pressure if you know that equilibrium concentration of the gas. So, here based on this Henry's law, that you can easily calculate what will be the partial pressure. Now, this concentration driving force or differences you can easily express in terms of pressure, partial pressure according to that Henry's law. Now, liquid mass transfer also you can assess by the penetration model. This is your penetration model as per physical liquid side mass transfer coefficient, individual mass transfer coefficient, that is KL, that will be 2 into 2 to the power d by pi t, where in this case d is the that size of that bubble, diameter of the bubble, and pi and tau is the residence time there. And also where in the gas liquid contact time or residence time, you can say that is defined by this equation here, that can be calculated, where V is the volume of the reactor, that is gas liquid mixer volume, and Qs is the volumetric flow rate of the gas, and QL is the volumetric flow rate of the liquid. If you know that these things, then you can easily calculate what is the gas liquid contact time. Once you know that gas liquid contact time and also size of that bubbles or slag inside the channel and equivalent diameter of that bubbles or liquid slugs, then you can easily calculate what will be the KL there. Now, once you know that KL in chemical process and also KL in physical process, then what should be the enhancement factor that can be calculated based on this equation there. So, there are some that mass transfer, individual mass transfer coefficient, interfacial area, and overall mass transfer coefficient for the different mixing devices here, as given by Ganapati et al. 2015. As per that and based on this table, you will have that you will see microreactor will give you that very high that mass transfer coefficient, even high interfacial area when individual mass transfer coefficient there compared to the others. So, that is why this micro channel based microreactors, why it is important for the process intensification there. And these are the some other comparison of that microreactor with different mixing devices, that in this case also you will see that very high specific interfacial area you can get for the microreactor, and also mass transfer coefficient there. And based on the different operating parameters, operating variables, then you can also have a correlations to calculate or predict that mass transfer coefficient. Based on this correlations as suggested by Ganapathy et al. They are in 2015 that you can predict that mass transfer coefficient in the channel by this correlation, where here B1, B2, B3, B4 are the coefficients, and these coefficients are given here in the slides. So, based on this equation you can easily calculate what should be the mass transfer coefficients for a particular operating conditions. So, I would suggest to go further about this through these references to get more about that hydrodynamics and mass transfer characteristics of two phase, even not only the gas liquid, even liquid system also you can have more information about that. So, I think you have that compact knowledge of that channel hydrodynamics and also what is that mass transfer characteristics there. So, this is the very preliminary idea of mass transfer as well as hydrodynamics there in the channel based reactor. So, it depends on that how you are actually developing your micro channel based reactor, and you once you develop that micro channel based reactor, you can study what should be that your mass transfer coefficient, what would be the effectiveness factor, what should be the frictional pressure drop, how that mixing characteristics can be effectiveness based on your pressure drop, frictional pressure drop, that you can analyze. So, that is why this basic or preliminary idea of mass transfer, even hydrodynamic characteristics are required for further development of the micro mixture, micro channel based micro reactor for the chemical engineering process intensification. So, I that will suggest to go further about that for your further more information and a better understanding of that. So, thank you for your attention.